Alright, so just a few properties I should mention before I state these fundamental theorems of calculus. So we talked about the definite integral in the last video, and essentially the definite integral is designed to model the area, the signed area bounded by a curve, on some closed interval in the plane, right? So there's a couple of obvious properties, one of which I already indicated geometrically last time, but here's some properties of the definite integral. So in particular, for say for f of x, a piecewise continuous function, I'll say that much, that's almost all we need. Piecewise continuous just means that it's continuous on each piece of the domain, and there's like a finite number of those. So it could have jump discontinuities, but not like vertical asymptotes or something, all right? It could have some holes in the graph, but those don't really matter. All right, so first of all, the one I already indicated geometrically, if m is less than or equal to f of x is less than or equal to big M, all right, for a less than or equal to x less than or equal to b, then of course m times b minus a is less than or equal to the integral from a to b of f of x dx. It's less than or equal to big M times b minus a. All right, so that's one property. Somewhat relatedly, suppose g of x is also piecewise continuous, all right? And if you have f of x, right, is less than or equal to g of x for a less than or equal to x less than or equal to b, it's fairly clear that the area bounded by g can be bigger than the area bounded by f, right? So then the integral from a to b of f of x dx is less than or equal to the integral from a to b of g of x dx. All right, so that's an important one to know. 3, this is kind of obvious. Once you know 1 and 2, or if you just know 1, you know, by the way, of course, the integral of the zero function from whatever to whatever is equal to 0, that's kind of like obvious. Whether or not I prove it for you, who cares? Well, I guess math majors care. But, you know, if the function, well, we could say this, the integral from a to b, right, of f of x dx is less than or equal to the integral from a to b of the absolute value of f of x dx, right? So if I replace the function with its absolute value, then whatever was counting negative signed area becomes positive, and clearly this is a larger thing. All right. Let's see here. Another property of definite integral that'd probably be good to know. If you have a is less than or equal to b is less than or equal to c, right? Then if you think about the picture, right? Something like this, a, b, c, it's fairly clear, I think, geometrically, that the area from a to b plus the area from b to c should be equal to the area from a to c. So that gives us the identity, the integral from a to c of f of x dx is equal to the integral from a to b of f of x dx plus the integral from b to c of f of x dx. All right, so that's a good, important property of the definite integral to know. Now, I actually have a proof of that in my notes for what it's worth, and it took me like a whole 3-hour faculty orientation section to work it out. I mean, it was, you know, one of my better faculty meetings. But it is technical, and probably it's not even wise to try to prove that at this level of theory. Probably that kind of thing is better left to, say, the context of measure theory and so forth. But let's see here. Those are some big properties. The other one I would be remiss not to mention is this sort of orientation of the definite integral. In other words, integral from a to b of f of x dx is equal to minus the integral from b to a. And so that in some sense is a definition. It kind of depends on what you take the definition to be, all right? You say, well, your definition assumed that A was less than B, so one of these things doesn't make sense, right? Well, okay, fine. So this is either a definition, or if you take the formula that I gave in the last talk here, this guy, if you take this formula as the definition, and you don't insist that A be less than B, I think all these formulas still make sense. And so you can have a definition when these are kind of backwards. I know, whatever floats your boat in terms of the definition. Bottom line is, everyone agrees that the integral from a to b of f of x dx is equal to minus the integral from b to a of f of x dx, all right? And one of these is sort of a natural thing, and the other one is unnatural. But still very useful, all right, because there's two major sub-theorems that come from this. For functions that are even or odd, right? If you have an even function or an odd function which is got a domain which is symmetric about 0, we have these lovely theorems. For instance, the integral from minus a to a of f of x dx is equal to 2 times the integral from 0 to a of f of x dx. Sometimes very labor-saving to know that, right? And for an odd function from minus a to a of f of x dx, well, that is a 0. So those are kind of really pretty properties of the definite integral as they apply to even and odd functions. All right. So those are the basic facts, and all of this is really just about thinking of the definite integral as calculating the area bounded by a curve. All of these things I've said are pretty geometrically obvious, and you can prove them if you are willing to work a little bit harder at the analysis. All right. So, what is the fundamental theorem of calculus? Well, I guess before I tell you that, I should really talk a little bit about what on earth is an area function. Area function. So, the idea here, right, is you've got some graph, all right? Got some graph, and I don't know, could be whatever, like that, and you've got some base point, all right, which I'll call A. A lot of times we take A to be 0, right? And then I'm going to use t as the variable now. I'm going to write the area function at time t, or at variable t, over here, all right, t. So t. And so the area function of t, which of course is, there's also an a dependence here in principle, is simply defined to be the integral from a to t of f of x dx. All right, that is going to give you the area what? From here? Just that area, right? Now, just to give you a little bit of sort of simple intuition for how the area function relates to the derivative, if we look at t plus delta t, right? Just a little bit further, what's the difference? We've added what? We've added this little orange strip right here, right? I'll crosshatch it. And so clearly, if you look at that, a of t plus delta t, right, should be equal to what? It should be equal to, well, on the one hand, of course, it's just the integral from a to t plus delta t. That's not too interesting, though. Well, maybe it is. Tell you what, I'll do that. Integral from a to t plus delta t, f of x dx, right? But of course, the property, what did I call it? Property numero 4, or quattro, or I don't know what the Portuguese is for it. Oh well. These Olympic Games make no sense to me. I don't know. But anyway, integral from t to t plus delta. So I've got two things, from here to here, from there to there. So of course, a of t plus delta t, what is that equal to? Well, that's equal to the integral from a to t of f of x dx, plus the integral from t to t plus delta t of f of x dx. All right. My color coding is not optimal here. So that's the brown part, and of course that's the orange part, right? Now, as I've defined it, this is equal to what? This is equal to a of t, right? Oh, my color coding is not strong today. So a of t, right, this piece, and then plus the orange part. Well, what is that? Well, the width of this is, right, width is what? Width delta t. What's the height of it? Well, I guess you could use anything here, 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 here. I'm just going to say, to good approximation, that's plus, you know, f of, I don't know, I'm going to be lazy, just use f of t. You could use f of the midpoint if you wanted. I mean, you like that would be more true. Yeah, fine. Yeah, you got me. I'm gonna be lazy. Like that, and then of course, that kind of tells you, right, what the deal is, because if we look at a of t plus delta t, right, minus a of t, and we divide that by delta t, what do we get? We get f of t, right? And then so as as delta t goes to 0, what's that quotient? Well, it's the difference quotient of a, right? We find what? We find that dA dt is equal to f of t. So the derivative of the area function with respect to time is equal to the integrand of the area at that time. And that, folks, is the fundamental theorem of calculus, part 1. Now, to prove this carefully, of course, you should do a little bit more work and blah, 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 blah. If you look at my notes, there's a lot of blah, 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 blah about this, and that's important, blah, 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 for you to see if you're a math major and so forth. But let me just state it here. So d dt of the integral from a to t of f of x dx, right, is equal to f of x. And there it is, that's FTC1 in a nutshell. Now, usually, a lot of times, we sometimes see the roles of t and x flipped around. I use t and x as I did because I think it's more geometrically natural for you to see in the derivation. But of course, operationally, this is exactly the same statement as d dx of the integral from a to x, right, of f of x dx. Oops, I can't do anything. Bar, oh well. Equals to f of x, or sorry, I was trying to do this and then my mind skipped. F of t dt is equal to f of x. All right. By the way, fun fact, I should mention at some point, the integral from a to b of f of t dt is just the same as the integral from a to b of f of Pac-Man. Pac-Man. I mean, this is a dummy variable of integration. It doesn't matter what letter you use here, it's just a shorthand for that infinite sum. So, you know, it's not t, x, u, v, whatever. All right. So there's FTC1. Now, FTC2. Now, FTC1, you're like, well, who cares the derivative of the integral? Is the function again like that? Well, and to be more precise, the derivative of the area function is the function of which you're finding the area under. Well, there are actually applications which define functions in terms of integrals with variable bounds, especially in optics, the Fresnel function, some other things. There is direct application for that idea, but you know, the FTC2, of course, is what's far more common to see application of. FTC2 simply states this: if f prime of x is equal to f of x, all right, for a less than or equal to x, less than or equal to b, then, punchline, the integral from a to b of f of x dx is equal to f of b minus f of a. Now we have symbols for this. We can also write this as f of x evaluated from a to b, like so. But there you have it. That's FTC2, which is very, very important to be able to know and apply, of course. So just an example, right? A few examples of this. If I want to calculate, say find area bounded by y equals x cubed from 0 to 2, then I calculate the integral from 0 to 2 of x cubed. Now x cubed is positive, or non-negative there I should say, so this is the area, not the signed area. We'll talk more about areas bounded by curves in a future video here. But so I need an antiderivative for that. In other words, this says find an antiderivative, take the value of the antiderivative at the endpoints, and that will give you the value of the integral. So this is 1/4 x to the 4th. I have to evaluate that from 0 to 2. When I plug 0 into that, I get nothing. When I plug 2 into that, I get 2 to the 4th, also known as 16. 16 over 4 is 4. So I get 1/4 of 2 to the 4th minus 1/4 of 0. Just to give you the steps, but the answer is 4. Which is not too shabby. I mean, goodness gracious, look at that's really fantastic how simple that is, right? Because y equals x cubed is this kind of grandiose function, and if you go from 1 to 2, right, we have just calculated not an approximation, but an exact account, right? An exact account of the area from 0 to 2, this area up in here, right? I mean, my graph isn't even accurate, but that is precise, the area. That said, I think you can, well, maybe we can even kind of understand that too, right? This is 1, 1, right? So, like, you got this piece over here, which is the area in here is certainly less than 1, right? And let's see here, this is what? This is 8, right? So this big box would have an area of what? Of 8. But you can see it should definitely be, I mean, 1 plus 8 is 9. I mean, 9 is obviously an overestimate, right? But I don't know. I can't see much more without, I mean, trying to understand intuitively why that makes sense without getting out some graph paper or doing something a little bit sneakier. All right, so there it is. Example 2. Suppose we want to integrate from, I don't know, -1 to 1 of, let's say, e to the x dx. So that's e to the x evaluated from -1 to 1, also known as e, right, minus what? E minus e to the -1. Huh. And, well, that's the answer, right? But kind of fun way to look at this is what? This is really 2 times what? This is 2 times 1/2 of that, which is 2 times the sinh of 1, for what it's worth. And so, I mean, this is a calculation probably only I would think of because I'm weird. But another way I could look at this, right? Kind of funny. -1 to 1, e to the x is cos x plus sinh x, right? And so cos is even, right? Sinh is odd. Don't forget the dx. The dx is not optional. It is, you must write it. If you don't write it, I will take off points. I don't enjoy taking off points, but I must. As my advisor once told me, if he didn't take off points, he didn't feel like he was really grading. I'm not sure I entirely believe that, but it is a good principle to live by. Anyway, this is an odd function, integrates to 0. That's an even function, so this is 2 times the integral from 0 to 1 of cos x dx, if you believe the property 5 part b or whatever I wrote. And so the antiderivative of cos is what? Excuse me, sinh. So I have 2 times the sinh of x evaluated from 0 to 1. Sinh of 0 is 0, so I get 2 times the sinh of 1 minus 2 times the sinh of 0, which is 0. So there you go. Now, which is the better way to do this integral? I think it's clearly in black, but I'm just illustrating how all things work together for good for those who actually know math. All right, anyway. Let's see, I don't think that's quite how the saying goes, is it? Let's see here. Example 3. All right, an example 3. Example 3. Suppose we want to integrate from 0 to 4 of 2x e to the x squared dx. All right. So this one, let's see here. So the two different ways we can go. The one way would be to notice that e to the x squared is an antiderivative for this, right? So if you notice that the derivative with respect to x of e to the x squared, right, is 2x e to the x squared, which you could discover using u substitution, right? Then you know that the antiderivative here is e to the x squared. That's my big F of x, and I can evaluate that from 0 to 4, and that will give me e to the 16 minus e to the 0, which is a very big number. So that's e to the 16 minus 1. All right, so that's one way you can go. In other words, if we know the antiderivative, then we can apply FTC2 directly, right? But what if we don't, right? If we don't, there's another way we can do this calculation, which does u substitution at the same time, all right? So integral from 0 to 4 of 2x e to the x squared dx. And so here's the u substitution with bounds, all right? So what we do is we say, okay, well, u equals x squared, right? du is 2x dx. That we all knew before, right? We talked about that in previous talk. And so that's great. So that gives us the integral of e to the u times du. So I changed the integrand, I changed the measure, just like we did before, but now we got bounds. So I also have to change the bounds. U of 0 is equal to 0 squared, otherwise known as 4. Like, good gracious, what is wrong with me? Otherwise known as 0. U of 4, right, would be 4 squared, which is otherwise known as 16. So once I write this du here, it has to have u bounds. The u bounds are 0 and 16. When I do this with the definite integral, I never have to go back to x, all right, unlike the indefinite integral with u substitution. I just have e to the u evaluated from 0 to 16. And of course that is equal to e to the 16 minus e to the 0, which again is just e to the 16 minus 1. All right. As a rule of thumb, I don't care if you simplify certain things, but there are certain things that sort of irk me. Like if you leave this unsimplified, I find this bothersome. If you do not simplify this, this annoys me. If you have things like, I mean, you get the idea. So this is troublesome to me. This is annoying. Anyway, so a sidebar. Anyway, I'm not too much of a stickler for simplification, but there are some basic things I'd like to see simplified. Okay. So that's an example of u substitution changing the bounds. Let's see here. All right. The the next fundamental theorem of calculus, and this is just my my silly interpretation. FTC3. What is FTC3? FTC3, in my estimation, is this: d dx, all right, of the integral, let's say from a of x to b of x, all right, of excuse me, f of t dt. All right, what is this equal to? Well, this is equal to f of b of x times db dx minus f of a of x times dA dx. So it's a variant of FTC1, and let me show you how I think of FTC as being derived from FTC2. So FTC2 says what? So here's a proof. I'll put it in quotes since there probably are some gaps here. But here's a plausibility argument at a minimum. So integral. The integral from a of x to b of x, all right, f of t dt. Well, that is going to be the antiderivative of f, which exists because f is continuous, I'm assuming that. And so we have f of, f of x evaluated from a of x to b of x. All right. That's by FTC2, right? And I guess it's by the application of FTC2 many, many times over, right, for arbitrary x. Now, that of course means f of b of x minus f of a of x, right? And what's the deal with big F? We're assuming big F prime of x is equal to f of x, right? All right. So we have this identity. Now if we differentiate that, right? If we differentiate that, we have the derivative. Where's this t coming from? X. So we have ddx of f of b of x, right? Minus ddx of f of a of x, but chain rule, right? So that's f prime of b of x times b prime of x minus f prime of a of x times a prime of x by the chain rule. But f prime is little f, right? So that's little f of b of x, and b prime, of course, is db dx. I'll just write it in the other notation. Minus f of a of x times dA dx. Getting rid of the primes. And there it is. That's exactly the claim of FTC3. Anyway, this comes up from time to time. Probably don't need it too much, but it's worth knowing. So just an example. I guess I'm on example 4 of this talk. Anyway, so example 4, if I was to say take the derivative of the integral from, say, x squared to e to the x of the inverse hyperbolic tangent of x cubed plus the sine of x. Oopsie, I was supposed to use a different variable of integration. Let me put some bars on it. Dx bar. All right, I shouldn't use the variable of integration, and the fixed but arbitrary x out here is the same. Anyway, so with that said, FTC3 is the hero. We simply do inverse hyperbolic tangent of e to the x quantity cubed plus the sine of e to the x times the derivative of e to the x, which is e to the x, and then subtract, let's see here, inverse hyperbolic tangent, and then I have to evaluate x cubed at x squared, which x squared cubed is x to the 6th. X to the 6th plus the sine of x squared times the derivative of x squared, which is 2x. So just to emphasize, this e to the x is precisely this guy. This 2x is conceptually this guy, right? So that's FTC3. All right. I don't usually see that written in calculus books. There's probably something technically amiss about it, but I'm not aware of a counterexample in it or any danger in saying it. And it will solve all the problems that are of this type. All right. So that's a quick review of how you calculate definite integrals, as well as how you do U substitution involving definite integral. Probably should do some more examples of that. So I'll pick that up in the next video, a few more examples. Oops. U substitution with definite integrals. Thanks, guys.